Hello, classes. This is Doug Schwartz reporting for section 4.3 exponential functions. This is college algebra. So let's have some fun with this section. Okay, so on Learn, you should have seen this sheet here. This is brand new stuff for us, exponential functions. I give the definition there. And notice it's of the form of f of x equals a to the x, where a stands for any positive number. And we don't like to have a as 1, because 1 raised to any power is going to be 1, and that would just be a horizontal line. So that's why we say this, then a is greater than 0. That's called the base. X is called the exponent. And let's see, the domain is nice. It's all real numbers for exponential functions as long as that base is positive. Okay. So let me just give an idea of what I mean by that. The base has to be positive for the domain to be all real numbers. So if you have something like this as your base and it's being raised to the 1/2 power, good thing to know, the 1/2 power is the same thing as the square root of. So wouldn't that then be the same thing as this? And we know the square root of -4 is not in the real number system. There's no number that when you square it will give you -4. So that's why this wouldn't be a real number answer here. But that's why we say that as long as the base is positive, then you avoid that catastrophe. So then we can say the domain, isn't the exponent the variable x, which implies domain? And see right here, it's a to the x. Or remember, domain and x are super related. So this x can be any real number as long as the base is positive. So, but if the base is negative, all of a sudden we can't let x be 1/2. Okay, anyway, let's continue here. All exponential functions have this shape to it, the graph. Notice for all basic exponential functions, meaning no transformations being applied, like you don't see a vertical shift here or a horizontal shift, or you don't see a reflection, no negative signs there. Remember, those transformations are very powerful. They work for all of these different functions, except for the polynomial function. So the basic one, it's always going to have that shape, where y equals 0 is always a horizontal asymptote. So notice this graph, as we go toward approaching negative infinity on the x-axis, it's never going to touch or cross that x-axis, which is the same thing as the equation y equals 0. And that's why we call that a horizontal asymptote. In other words, no matter what real number you plug in for x here, when you raise 2 to that power, you'll never get 0 or a negative answer. Like, how about 2 to the -100? What do you think? Maybe that could be 0 or a negative number? Let's find out. Okay, what happens if you let x be -100? And we haven't formally gone over some of these rules of exponents, but I'll just jump ahead here. When you have a negative exponent, how do you handle negative exponents? You do this. You flip the base. Right now that base 2 is in the numerator, so put it in the denominator, and then make that exponent, whatever it is, positive. So this does equal that. Here's the general rule to show that. A to the -1 equals 1 over a to the +1. So that's one of the rules with exponents. And so then, indeed, this is true. And then, isn't 1 a positive number? And isn't this denominator? It's a huge number, but it's also positive. What's a positive divided by a positive? A positive, which means it's greater than 0. So that's why you can never get the answer, which is like y, to be 0 or negative. That's why over here, this graph will never touch y equals 0. The answer can never be 0 or negative. Notice the graph supports the algebra. What are some other characteristics of all basic exponential functions? The domain, as we stated before, is all real numbers. The range, 0 to infinity. Notice it's a rounded parenthesis here because you can never get 0 as an answer here. or you can write it as y is greater than 0. No equal sign, though. The horizontal asymptote, again, is y equals 0. Vertical asymptote, there is never a vertical asymptote with an exponential function. Because isn't the domain all real numbers? Remember I've said in class that the vertical asymptote and domain are super related, so that makes sense. And notice this is an increasing function. So all basic exponential functions, as long as that base is higher than 1, it will always be an increasing function. Notice as the x's get bigger, the y's are getting bigger. So it's an increasing function. And look at the end behavior. As x goes to infinity, what's happening to those y coordinates? Well, it looks like they're approaching infinity. Let's see that. As x is approaching infinity, what's happening to those y coordinates on the graph? Aren't they going toward positive infinity on the y-axis? And what about as x goes to negative infinity, y is going to 0. So as x is going toward negative infinity, what's happening to these y coordinates on this graph? Aren't they getting closer and closer to y equals 0? So y approaches 0. Remember, with the rational function, wasn't the end behavior? These two numbers were always the same. But this is the personality of the exponential function. As I've said before, this algebra course that we're taking has a lot of different functions that we uncover, we go over. And each one of these functions has their own personality. Okay, now notice here, this example here, sketched a graph. It looks like this basic exponential function, notice it's the same base. But we got transformations here. Vertical shift, a reflection about the x-axis, since that negative sign is outside the function. If the negative sign were right here in front of that x, it'd be a reflection about the y-axis, because it's kind of inside the function. By the way, if this were like a 3 to the x, this graph would be steeper. The bigger the base, the steeper the graph. And I don't want to spend too much time on this because I want to go over 2 other examples here. But notice we just do this in stages. Well, I didn't even graph it actually here. But you start off with y equals 2 to the x, which looks like that. And then let's do the vertical shift last. So here then you would reflect this about the x-axis. So what would that look like when you reflect about the x-axis for that graph? Let me do it real quick here. Here's y equals 2 to the x. What is that graph going to look like when you reflect about the x-axis? Like this part's going to go down here, and that part's going to go down here. So I think it's going to look something like this. Let me think for a moment here. It's going to look like that. This would be y equals negative 2 to the x. Remember, the priority thing, the exponents comes first. So this is 2 to the x, and then you do that first, and then a reflection about the x-axis. Still the same y equals 0 horizontal asymptote. And then the vertical shift, and then you would drop it down 1, so the final graph would look like this. Vertical shifts, this is y equals negative 2 to the x minus 1. Vertical shifts does affect a horizontal asymptote. This was still y equals 0 for the horizontal asymptote. Now it's draw it in, and y equals negative 1 is the new horizontal asymptote. Because remember, vertical shifts affect previous y's, and isn't this a y equals 0? So now it becomes a y equals negative 1. Subtract 1 from all previous y's. Okay, anyway, let's see what else was on this lesson plan here. This was a tough problem. Exponential equations. We've never seen exponential equations before. We've done linear equations. Those are kind of simple, like about 3x plus 1 equals, say, we'll say 19. Solve for x. This is an example of a linear equation. So subtract 1 from both sides, and you get 3x equals 18. And then divide both sides by 3, and you get x equals 6. So that's an example of a linear equation. And we've also done quadratic equations, which are something like, say, x squared minus x minus 6 equals 0. There's a typical quadratic equation, and we know how to handle those too. You factor it. That would be x minus 3 times x plus 2 equals 0. And and then use the zero factor property, and you get x equals 3, x equals -2. So that was just a little review there. But now we're talking about exponential equations, and this has its own personality. It's a whole new ball game. So how do we do these exponential equations? Let's start off with an easier one. How about something like 3 to the x equals 27. This is an example of an exponential equation. Equation because we have an equal sign, and exponential because whenever you see the variable in the exponent, you know you're looking at an exponential equation. So we can tell by inspection. It looks like x equals 3. Doesn't 3 cubed equal 27? I could have done this though. 3 to the x equals 3 cubed. Isn't that the same thing as 27? And this is how we solve exponential equations. You want to get it like this in bare bones. And notice we got the bases are both the same. They're equal to each other. So what does that mean? Then the exponents have to be the same. So then from here, you set the exponents equal to each other because they have to be the same. And we get x equals 3. Done. We got x by itself. And notice we said before x equals 3. So there's a good taste of how you solve an exponential equation. What would you do, though, if 27 were not a power of 3? Then you would need logarithms. Logarithms unlock the exponent. But for this section, we're nice and homemade where this is going to be a power of that smaller base. So in that case, think of this idea. You want to get it to this nice idea, and then you set the exponents equal to each other. Okay, let's look at this next one here in the notes. Let's see, right here, solve the exponential equation. So how are you going to solve this? I see the variable x, it's in the exponent, so it's an exponential equation. I like how 27 is a power of that smaller number 3. Always first see, can you write the bigger number as a power of that smaller number? So that's what we're going to do next. Let's do a property of exponents, by the way. When you have a power to a power, the rule is you multiply the exponents. I wrote that in the notes. Let's see if I can find that. Yeah, right here. Isn't this you got to identify what you're looking at. Isn't this a power? Right there. And isn't that a power? A power to a power, you multiply the exponents. So you rewrite that base 2, and then what's 2 times 3? 6. And that equals 64. So that's the final answer for solving this. Simplifying, what is 2 squared all to the third power equal? It's a power to a power, so multiply the exponents. So that's where that 6 comes from, because that 2 times that 3 is 6. And 2 to the 6th is 64, because what's 2 times 2 times 2 times 2 times 2 times 2? 64. We could check that by using the order of operations. Do the stuff in the parentheses first. What's 2 squared? 4. And what's 4 to the third power? 4 times 4 is 16. And 16 times 4 is 64. So these rules do work indeed. So let's go back to this problem we were just doing right here. We want to solve this for x. So first thing I want to do is simplify the left-hand side. Isn't this the same thing as that? Because I recognize this as a power to a power, and one of the rules of exponents, there's about 7 of them, of these rules, is when you have a power to a power, multiply the exponents. So we have this now. And I wrote 27 as 3 cubed, so isn't this equivalent to that? Same thing indeed. Indeed. Okay, next. I want the bases to be in the numerator. This base 3 in the denominator doesn't help much. So let's use another property of exponents, which I already talked about with the negatives. So let's write 3 to the 2x over here like we did. Equals, and then instead of writing 1 over 3 cubed, isn't 1 over 3 cubed the same thing as 3 to the -3? Very interesting. Because if you're not sure about that, just look at 3 to the -3. Isn't 3 to the -3? How do we handle negative exponents? You flip over the base, so make that 1 over 3, and then make that exponent whatever it is positive. So we got to get used to these negative exponents. So this is the same as that now. And now we're in that special place. It's bare bones. You got the same base. They're equal to each other. So that means the exponents have to be the same. So this is a wild step. You set the exponents equal to each other. 2x equals -3. Now it's a linear equation. We know how to solve a linear equation. Divide both sides by 2 and you get x equals -3 halves. Done with that problem. So very fun. Let's do another one. How about this exponential equation? Again, it's an exponential equation because I see a variable in the exponent. That's the exponential part, and equal sign means equation. So it is an exponential equation. Let's solve this for that x there. We got to obey the order of operations. It's tempting to use a distributive property and say, oh, 9 times 3 is 27. But you can't do that. The order of operations says exponents comes first. So that's why in the solution, I just wrote that 9 again. 9 times 3 to the x. But now I can use a distributive property here. What's 9 times 1? 9. So isn't this the same thing as that? Sure. Equals 9 plus, okay, we got the square root of 3. Remember I said at the top of the broadcast, the square root is the same thing as 1/2? Because there's an implied exponent of 1 here, and the root is implied to be 2. So you can write a radical as an exponential, a rational exponential. So it's always the exponent over the root. Think of a tree, the roots are in the bottom. And isn't that root 2? That's where that 2 comes from right there. Okay, so far we're making progress. Next step. Let's subtract 9. We want to make this x term, we want to isolate it. So let's get rid of that 9. Subtract 9 from both sides then. From both sides, and you get this equals that. Now, we can't multiply that 9 with the 3, but we can be crafty. Let's write 9 as 3 squared. So we get 3 squared times 3 to the x equals 3 to the 1/2. And now here's another rule of exponents. When you have like bases with exponents, you rewrite the base and add the exponents. What's 2 plus x? 2 plus x? You can't, those aren't not like terms. So we have this, and now aren't we in that special place? The bases are the same. They're equal to each other. So the exponents have to be the same. So set the exponents equal to each other. And now it's a linear equation, and then solve for x and you get that. The number e is an important number, probably the most important number in mathematics. They call it the natural exponential. Sometimes it's called the natural base for a logarithm too, as well. So we have that. And what is e? It's just an irrational number in between 2 and 3. It's 2.72 rounded, but the decimal expansion goes on forever. And here's the calculus definition right there. E equals the limit as n approaches infinity of 1 plus 1 over n to the n power. And don't be intimidated by e. Notice y equals e to the x. Isn't that base bigger than 1? So that means it's an increasing function. And as you can see right here, we've got y equals 2 to the x, y equals e to the x, and y equals 3 to the x. And isn't e in between 2 and 3? That's why it's in between those two functions. But notice they all have the same y-intercept of 0, 1. I don't know if I mentioned that before. That's another characteristic of all exponential functions. They have a y-intercept of 0, 1. It makes sense. Because if you got x equals 0, what's 2 to the 0? 1. What's e to the 0? 1. What's 3 to the 0? 1. So they all go through that y-intercept of that. Let us know if your base is less than 1 and bigger than 0, because we want the base to be positive. So for example, let's take a look at over here. Well, let's see if I can find it. Let's see, where did that go? Y equals right here. Notice, isn't that 1/2 to the x? Isn't that base smaller than 1? So it's going to have a lot of the same characteristics as any exponential function, any basic one. It's still going to have 0, 1 as a y-intercept, still going to have y equals 0 as a horizontal asymptote, but it's going to be a decreasing function. So notice, if you have y equals 1/2 to the x, that's the same thing as that, by the way, because what's 1 to the x power? That's another rule of exponents. If you have a fraction being raised to a power, you raise the numerator to that power and the denominator to that power. So 1 to the x, 1 to any power is just going to be 1. And then 2 to the x, well, there it is right there. And isn't this the same thing as that? That's how we handle negative exponents. For instance, what's y equals 2 to the negative x? How do you handle that negative exponent? Flip over the base, put it where it ain't. Right now it's in the numerator, so put it in the denominator, and make this exponent, whatever it is, positive. So, yeah, so notice if you have a negative exponent, that's the same idea as kind of like if you have a base smaller than 1. So gets a little time to get used to this idea. And notice, isn't this a decreasing function? As the x's get bigger, the y's are getting smaller. Okay, let's see. Here's some rules of exponents. I chose the base e because e is such an important number. So let's look at this one. How do you handle, what is e to the negative 2 times e to the 5th? Well, that's one of the rules of exponents. How do you multiply like bases with exponents? You rewrite the base and add the exponents. What's negative 2 plus 5? 3. That's why the answer is e cubed. What about b? How do you divide like bases with exponents? These rules of exponents only work when you're talking about like bases. And notice we have e as the base for both numerator and denominator there in part B. So how do you divide like bases with exponents? You rewrite the base and subtract the exponents, top minus bottom. What's 7 minus a negative 3? Positive 10. So that's why that answer is e to the 10th. And then part C, isn't that a power to a power? So you just multiply the exponents. So that's going to be e to the 20th power, which is again roughly 2.72 raised to the 20th power. And that's a pretty big number. You know, it could be close to a million. Let's see, here's a real tough example. Again, it uses a lot of the properties of exponents. Notice that, notice that 1 over e cubed. I don't like how that e's in the denominator. So isn't 1 over e cubed the same thing as e to the negative 3? You got to be crafty. And, you got to use your rules of exponents to your advantage. Make it work for you. And then now, don't we have like bases being multiplied with exponents? So you rewrite the base and add the exponents. What's 2x plus negative 3? 2x minus 3. And now, aren't we in that special place? The bases are the same. They're equal to each other. So therefore, the exponents have to be the same. So that's what you want here. Now you just got a quadratic equation. So that's good enough for that one. What about this one here? I can tell it's e to the 0 equals 1, so x has to be 0. But if you wanted to, you could have rewritten that one as, how about e to the 3x equals, instead of writing 1, how about be crafty and write e to the 0? Isn't e to the 0 the same thing as 1? Now, aren't we in that special place? The bases are the same. They're equal to each other. So the exponents have to be the same. Again, this is how exponential equations work. That's what you want to get to, that Garden of Eden idea, where the bases are the same, they're equal to each other, so the exponents have to be the same, so set the exponents equal to each other. So you get 3x equals 0, divide both sides by 3, and you get x equals 0, as we said 1 minute ago. And then what about this last problem here? How do we solve that one? Well, let's see, we got e times e to the x equals the square root of e. We want to solve that for x. We notice the answer is x equals negative 1/2. Let me show the work, though, which I'll do over here. So notice I just rewrote the problem. Let's see, this one's a tricky one. You have e here, and they're like bases with exponents, so I can multiply that. How do you multiply like bases with exponents? You rewrite the base and add the exponents. What's the exponent of this e? 1. So I'm going to put that in there, make it look easier. So now, what's e to the 1 times e to the x? Isn't it just going to be e to the 1 plus x, or x plus 1? Addition's commutative, it doesn't matter. So again, how do you multiply like bases with exponents? You rewrite the base and add the exponents. Okay, equals the square root of e. Again, you got to be crafty here. And I'm going to rewrite that as e to the 1/2 power. That's the same thing. That 1/2, I should have written it a little higher up and smaller. That's an exponent there. Now, aren't we in that special place? The bases are the same. They're equal to each other, so the exponents have to be the same. So now my next step is going to be this. X plus 1 equals 1/2. It's a wild idea with these exponential equations. That's how you handle them. You want to get to this place here where it's the Garden of Eden. The bases are the same. They're equal to each other, so the exponents have to be the same. So be aggressive and set the exponents equal to each other. And now we're just a linear equation, and we can solve that easily enough. For x, subtract 1 from both sides, and you get x equals negative 1/2, as we said before. X equals negative 1/2. Final answer. Okay. And let me just do 2 more examples here. Let's look at this one here. So solving some exponential equations. Let's do some more of them. These are a little bit tougher. How would I do this one here? Well, let's see. I'm going to rewrite. I see the base. I like how that 4 can be rewritten as a power of the smaller base. So let's do that first. So I'm going to rewrite the 2 to the x equals 2 to the 3x times. Instead of calling that 4, isn't 4 the same thing as 2 squared? And I got to preserve that square right there. So we're making progress on this step. Next idea. Let's rewrite the 2 to the x equals, drop down the equal sign, 2 to the 3x, and let's simplify this factor. Remember, a power to a power, you multiply the exponent, so isn't that 2 to the 4th? Yes, indeed. Okay, let's keep simplifying here, because we're not in that special place yet. It's not compact like a Volkswagen here. Okay, so let's continue then. So 2 to the x equals, I want to simplify this right-hand side. We know how to multiply like bases with exponents. You rewrite the base is 2, rewrite the base, and add the exponents. So we have that. Now we're in that special place, the Garden of Eden. Isn't it compact like a Volkswagen? So the bases are the same, they're equal to each other, so the exponents must be the same. That makes sense. So be aggressive and set the exponents equal to each other. That's the next step. That's how we handle solving exponential equations. Now it's a linear equation. So we got variables on both sides. Let's get rid of one of those variables. Let's subtract 3x from both sides. So now we have this. Divide both sides by -2, and there's the answer. And if we want, we can check it. Let's do it over here. So start with the original equation. Let x be -2 since that was our answer. And does 2 to the -2 equal, I put a question mark there just to be humble. Maybe my answer was wrong. And then 2 to the 3, instead of writing x, we're going to let x be -2. Notice this is 3 times x, so that's why it's 3 times -2, and then times 4 squared. So let's see if this holds true. Does the left-hand side equal the right-hand side? If it does, then we solved correctly. 2 to the -2, that's the same thing as 1 over 2 squared, right? That's how we handle negative exponents. You flip over the base and then make the exponent whatever it is positive. Equals 2 to the, what's 3 times -2? -6? This has nothing to do with the rule of exponents here. I'm just plugging in. Okay, and then 4, isn't that the same thing as 2 squared? And then that square 2 there, I just drop that down. And then 1 over 2 squared, the same thing as 1/4. Does that equal 2 to the -6 times 2 to the 4th, right? A power to a power, you multiply the exponents. What's 2 times 2? 4? Okay, next. I wrote 1/4 as 2 to the -2. I should have just left it as 2 to the -2. It works better that way. So 2 to the -2. Does that equal, how do you multiply like bases with exponents? You rewrite the base and add the exponents. And then we get this. 2 to the -2 equals 2 to the -2, right? Because what's -6 plus 4? -2. So that indeed is true. So it's a good check. I feel confident that answer is right indeed. How about this final problem now? Here is another exponential equation. It's good to be able to identify what you're looking at. And this is an exponential equation, because I do see an equal sign and I do see variable in the exponents. So exponential equation. So I like how that base 8 is a power of that smaller one too. Power of that smaller base. So I'm happy about that. I don't need logarithms then to solve for this. So let's rewrite the 2 to the x equals, let's write 8 as 2 cubed to the 5 minus x power. So again, I rewrote that base 8 as the equivalent 2 cubed. And I put it in parentheses because that's the base being raised to that power. So this and this, they're equivalent steps. And then 2 to the x equals a power to a power. You multiply the exponents. So 2 to the 15 minus 3x. It's kind of like the distributive property. What's 3 times the quantity 5 minus x? Because it's a power to a power, you multiply the exponents. We have that. Now we're in that special place. It's compact like a Volkswagen. So from here we go set the exponents equal to each other. And then we have this. Yeah, it's easy to solve from here. It's just a linear equation. And I wrote the check right here. And I'm going to end the video right now. So that is all. And goodbye.